see where our transformations were. Christian, did you have a specific one you wanted to look at? 5. Okay? In 5, and we did this one in class, you had to make sure you first raised to the power. So it was 9x squared. So that gave you your chord graph of a quadratic. Now, it's doing a dilation here. It's doing a stretch. They do a horizontal compression. I say vertical stretch. I remember the other day, a vertical stretch by a factor of 9. Theirs is wrong. Theirs is wrong. Because it's not a factor of 3 either. It's a factor of 9. Or actually, theirs would be a compression by a factor of 9. Well, here's the difference. Here's your chord graph. Okay? Here's x, and y is equal to x squared. And here y is equal to 9x squared. Well, let's just take a couple of points. 0, 1, 2. If I square 0, I get 0. I square 1, I get 1. I square 2, I get 4. That gives you your regular parent graph. If I'm looking at the 9, what the 9 says is, go ahead, square it, and then multiply this by 9. I still get 0, then I get 9, then I get 36. Look at the distance that changed. This increased. Instead of 1, 1, I'm now 1, 9. Instead of 2, 4, I'm 2, 36, way up here somewhere. I've stretched my graph. I pulled it up vertically. I changed the distance to 0. I increased it. So if this number, let's call it A, if A is greater than 1, you have a vertical stretch. Where they get their horizontal compression is, there's 2 ways to look at it. You can move it vertically, stretch it, or horizontally, if you took your hand like this around your graph and you squished it in, there's your shrink, there's your compression. So horizontally, you're compressing. Vertically, you're stretching. So we agreed the other day, we would only go with the verticals in here, because I don't want you to be confused on when I do a stretch and a shrink. Because if I'm talking vertical and you're talking horizontal, we're exactly the opposite. So we're going to do a vertical stretch by a factor of 9. Because what it did was it changed your distance to 0. It changed your y distance. Okay? And they probably did the same. Oh, they did a vertical stretch for that one. Anytime you're inside the parentheses, they usually do a horizontal. But we're just going to get rid of the parentheses and keep it a vertical. We're going to get rid of our parentheses and keep it a vertical. Inside, they usually say horizontal, but we're going to just call them all verticals. Get rid of your parentheses and be vertical. This one too, no parentheses on number 10, so they have the vertical. I say shrink, they say compression. That's really, that's up to you. I use stretch and shrink just because it's easier. They use compress, and they use stretch when they do a stretch. So, I guess they use both. They use their vertical stretch and a vertical compression, then I use a shrink. If you're going to use a stretch, use a shrink. We okay with that? All right, let me bring this down, if I can. Oh, yeah. Okay, this morning it wouldn't go down, it wouldn't drop down for me. So the last few, these are important because you had a lot going on. 12, 13, 14 had a lot going on. Start inside your parentheses, move out. So starting here, I have a horizontal shift rate, 1 unit. I come out, I have a vertical stretch by a factor of 3. They also did most of them in the right order. Then lastly, I have a vertical shift by a factor of 1. I want it in the right order. Cubing works the same as the squaring. You have a horizontal shift left 9. Then you have a dilation, a factor of 2, vertical stretch. Then you have a reflection. You never have a negative stretch or a negative shrink. And then you have a vertical shift down. And I think 14 we didn't class. It's next to the X, so that's a horizontal movement, and then a vertical drop, vertical shift down. Yeah. Okay, then here's the difference. See where this negative is? It's not near the X. So on your graph, if it's near the X, go like this. The X is going positive to negative. There's your reflection. If it's not near the X, it's actually just affecting your Y. So Y is positive to negative. They should have a reflection over the X-axis. Your Y goes positive to negative. That's over the X-axis. When you get this answer, whatever your answer is, then you multiply it by your -1. It didn't change your X, it only changed your Y. So technically your X, -Y. Just your Y's, so your Y goes from positive to negative, it's a reflection in your X-axis. Kind of like your intercept, it has a different effect. Okay? You good with that? Questions on any transformations? No? Okay. Today is your last topic. And we're going to do adding some functions. We're going to work with your functions, and we're going to do some basic operations on them. Adding them, subtracting them, multiplying, dividing them. So we can perform operations on your functions. Just as you did compositions of functions, right? You did your function notation, you did your composition of functions. We can perform operations on these guys. So we're going to start real basic. You have 4 operations that we're going to do. We're going to sum them. So it's kind of written almost like your compositions, but they have your operation in it instead. Here's your minus. And the multiplier row is a multiply, and then a divide. So you're going to just add your 2 functions. You're going to subtract your 2 functions. You're going to divide your 2 functions. You're going to multiply your 2 functions. The subtract, be careful. The subtract, you're going to have to use distribute the negative. On a basic, here's 2 functions, an F function and a G function. So if I just want to perform the addition operation on these 2, I'm taking my f of x, and I'm adding my g of x. So I take whatever I have for f of x, and I add g of x to it. I'm not solving anything. I'm going to come out with an expression here, because it will be the equation of my addition of those 2. So collect your like terms. 2x and a 2x give me 4x, and the 1's cancel out. So the sum of these 2 functions is x squared plus 4x. Just like you did your compositions before, you could take a value of x, and in this case x is 2. We could put x in here and in here, and then we can add those 2 together, or we can put it once into this equation and come out with the sum and not have to do them twice. So we're going to plug an x in for this. So we get 4 plus 8. We get 12, right? Now, watch. Everybody's giving that person away. So watch. If we plug the 2 in here, 2 times 2 is 4 plus 1. This would have been 5. 2 squared is 4. Plus 4 is 8. Minus 1 is 7. And isn't 5 plus 7 12? That's the same we get down here. It works like your compositions do. Only now you're just performing operations on them. The trickier one is the subtract, because you have to remember your parentheses. You have to take whichever one is first and subtract all the terms of the second one. That's a subtract sign. Minus So therefore, that means distributing that negative sign. So I would have to distribute this negative sign before I collect my terms. Because you're subtracting that whole function, not just part of it. So now, out comes your two x's. And you get negative x squared plus 2. Okay? So subtract, just be careful that you remember your systems. Good? Alright. The multiply, you might have to distribute, do a little bit of multiplying. The tricky one too is the divide. The divide usually ends up giving you a domain restriction sometimes. If we look at these two, if I'm just going to divide f of g of x there, I'm going to take my f of x divided by my g of x. Now, neither one of these functions has a domain restriction, right? But watch what happens when I go to divide them. Do I have a domain restriction now? Where? Denominator. My denominator cannot be 0. So even though my two functions did not have a domain restriction, I have to say, okay, set this equal to 0. I'm going to have to factor, and I have to do the quadratic on that, and find out where my allowable domain is. Anytime you divide, you may change your domain restriction. In this case, we didn't have one, and now we will. We'll end up having one. I have to do the quadratic to complete the square on that, so we're not going to do that part. But this one's a little bit more involved because this one has two radicals to start with. So I have to look at my domain for those two radicals. We know under a radical cannot be negative. So just to find my domain, I say x greater than or equal to 0. It might be my iPad that's doing that. Is it mine or is it somebody else's? Okay. Now, the second one says 4 minus x squared greater than or equal to 0. God bless you. Remember what your quadratics. This is why I kept impressing upon you. Your quadratic works differently. You're going to take your factors, set them equal to 0. You're going to find your critical values, plus or minus 2. Let me change my pen color. Now, plus or minus 2 is right here. Okay, they're closed. My parabola is opening down. So where is my positive? Right in the middle, right? Now, your domain for both of them has to be where they overlap. It has to be right here. So your domain for these two functions is from 0 to 2. That's all we can use. If we use to the left of 0, -1, this guy won't work. If we use out here, say 4, this guy won't work. The second one won't work. So the domain for this whole combinations of functions is from 0 to 2. That's all I can use. So now I go to set up my divide. My divide says, okay, f of x over g of x. So I take my f function, I take my g function. Now the nice news is, when you get to precalc, you don't have to rationalize any of your denominators. They stay the way it is. Even if I combine them under 1, there's nothing I can reduce, so I leave it like that. However, because now I have a radical in the denominator, didn't I give another restriction? So I want you to think a minute on how is that domain going to change? What is it, Whitney? Oh, okay, I thought you had it. It has to be greater than 0. This has to be greater than 0, but not equal to 0. So how will this domain change to fit, to accommodate that extra?
On the 0.
Good. Not on the 0, though, on the one that makes this 0. Which one's going to make it 0? 2. So the domain for this guy is going to have the soft bracket on the 2. See how that changed? We added one more restriction. We said, whoops, it cannot be equal to 0. So that affected this quadratic, which was my 2 and negative 2, right? Now they have to be open circles. Say we did the divide the opposite way. G of x over f of x. The g is this guy. The f, this one. I still don't have to rationalize. I can leave it like that. There's nothing else I can do. That would be my answer. But going back to my original domain, my original one was from 0 to 2 inclusive. What would my new domain have to be? Good. Soft bracket 0, because the only thing now you're telling me is, whoops, that can't be a 0 as well. So the divide one is a little trickier. You have to watch what ends up in your denominator. We would have had to do your domain restriction, whether we were adding, subtracting, or multiplying. But the divide one, you always have to go back and revisit in case you created another restriction in your denominator. Make sense? I know this is a little heavy for a Monday, but hang in there. Okay. Again, when we look at the domain of a composite function, we have more than one function. Therefore, we have to look to everybody's domains. We have to make sure we find one domain that accommodates all the functions. So we look at each one. Enter f of x. Does that have any domain restriction? No, none. It's a parabola, all real numbers. Your g at x. Does that have one? Yeah. So it's got a radical. So we say, okay, under the radical, it has to be greater than or equal to 0. There's your quadratic. So you're going to factor. Set your factors equal to 0. Find your critical numbers. Which way is this parabola opening up? Which way does it open? Up or down? Go to the number in front of x squared. It's negative, so which way is your parabola opening? Down. So we're solid here because it's equal. We're opening down. We're looking for wherever it's positive. So again, see where your positives are up here? And your negatives? Remember us doing this? I said you're going to use this one the most. So your domain is from negative 3 to 3. So when we, yes? But because we did that, we said greater than or equal to 0. We said we can only use positives and 0. That's why we're looking for the positives. So now, when you go to find this composite one, composition of functions, we take your g at x, and we roll the g into the f at x. We take this whole thing and we stick this in for x. Squaring it. When you square a radical, out it pops. And we can take away your 9s. At this point, you need to look. Did you give any further restrictions? No, there's no restriction to that part. So our domain stays at -3 to 3. Even though this looks like it has no restriction, it did when we started it. So we keep our final domain. So our domain stays at this. This is a great exercise in working with your domains. And you only have your 3 restrictions still. Fraction, radical, radical under a fraction. Okay, and here's a little thinker for you. I have a composite function, and I want to identify 2 functions that this came from. In other words, find those 2 that made this be equal to this guy. Find me the 2 parts. Does anybody have a possibility here? No possibility. Okay, so let's see if Raven's works. She's taking her G, and she's plugging it into her X, wherever X is. So it looks like that works. Good. Anybody else? No? How about so I'm going to take my G and I'm going to put it into this guy. Would that work too? Mm-hmm. So just a little, thing to think about to see which way it would work. That we can read off the graph and see if we can do our operations right off the graph. Remember, when you're looking at the value of a function, you're giving an x and it's returning a y. The value of the function is your y. So if I'm looking at my f at x when x is 0, what's the value of f at x when x is 0? What's my y value when x is 0? 2. In the G, that's the bottom equation, what's my y value when x is 0? -1. And now I just have to add them. 1. So it's the same process. Whether I'm subtracting, adding, multiplying, or dividing, I have to find the part and then do the operation. So when x is 1, on my f at x1, what is y? 3. When g is 1, what is y? 0. And I add them. I might have had to subtract them. In which case I do 3 minus 0. I might have had to multiply them. In which case I do 3 times 0. Or I might have had to divide them, in which case that would be undefined, right? So back to your addition. When x is 2 for the f equation, what is the y? 1. When g is 2 for the g, when x is 2 for the g equation, what is y? Yeah, that. And then add. And the last one. For the f equation, when x is 3, what is y? And for the g equation, when x is 3, 0.